What is up, guys? Welcome to another video brought to you by The Simple Engineer. In today's video, we are going to be talking about algorithmic mental models, and the algorithmic mental model that we are going to be covering today is the idea of the sliding window technique. This is a really powerful mental model to have in the back pocket of your algorithmic utility belt because it's really useful for solving a wide variety of problems. Now, you're probably going to hear me say the term mental models quite a bit, and the idea that I want to elucidate is that we are trying to devise a mechanism for recognizing a breadth of problems that we would deal with in application or in different environments for different types of problems or questions or algorithms, not the specific question itself. We don't want to memorize an algorithm. We don't want to memorize a solution. We want to memorize the mental model, or at least understand the mental model from a more conceptual point of view. That way we can apply our knowledge to a broad range of problems. That's exactly what I want to ingrain into the brains of those watching this video. So in this video, we're gonna talk about, of course, what sliding window actually is. We'll cover the benefits of why you would want to use something like this versus a traditional naive or brute force approach. We'll talk about how to spot these types of problems. What are some of the keywords or types of questions that you would see that may lead to utilizing this type of technique. And then we'll go through a variety of examples and their associative implementations in Java to really kind of pound these ideas into your brain so you can recognize them from a more broader point of view. So before we dive any further, let's talk about what sliding window actually is. The best way to understand sliding window from the highest, most abstract level possible is to imagine two shapes. The first shape is going to be the rectangle that you see on the screen, and this rectangle could represent an array, it could represent a linked list, it could represent really any arbitrary buffer of data that contains sequences of data that are contiguous or adjacent to one another. So the best way that you can imagine this is really maybe an array of characters or an array of integer values. And what we do is we basically slap a window at some subset of this array, and we start to ask questions. So whatever the question is that we're presented with, we're trying to optimize something, right? And so what we're optimizing, whatever it may be, we basically ask the question, is this the best that I can do? Maybe it is, maybe it isn't. We record that value, and then we kind of slide the window over. And we say, hey, maybe this is better. Maybe we can do better in this subset. Then we get to this point and we say, oh, hey, this is the best that we've seen thus far. It beats out all previous values that we have recorded, whatever it may be. So I'm going to record this one as my max, and I'm going to continue sliding it over. This one is worse. I do nothing. I continue sliding. And then I reach the stopping condition, which is the end of the data structure, and then I stop. And then, the hopeful thing is that I've stored whatever value that I'm trying to optimize against in some auxiliary data structure or some additional variable, and I return it from the function that I am working in. Now, this is the idea of the fixed-sized sliding window technique. There is an alternative approach to this, and it's known as the dynamically resizing sliding window, and it essentially basically grows in the same way. We're growing the window. It's sliding it's slightly different because the window is growing. There is no fixed size. But on the left-hand side, you'll see if we reach some criteria, we actually shrink. So it almost kind of looks like a caterpillar working its way across of a tree. We grow and shrink, and eventually we grow to the point where we reach the end of the array, and that's kind of our stopping criteria. And it's not that we choose one or the other, it's that we basically have different questions that we're trying to solve. So maybe the dynamically resizing approach is appropriate for one type of question, and the fixed length size is appropriate for another. And that's typically a dead giveaway based on the problem that we're seeing. And we'll look at both of these types of categories very shortly. But now the question that you may be asking is, why do we even want to do this technique? maybe what's the alternative? What was I doing? Well, there's a really naive way that people like to look at these problems, and it's the brute force approach. And typically what people do is they have an array like so. And what they'll typically do is they'll start at an index, and they will enumerate all possible combinations of the given criteria. So they'll start here, and they'll say, I'm going to iterate through, index 0, 1, 2, 3, 4. And then what I'm going to do is I'm going to go to the next index. And what I'm going to do is I'm going to start at 1 now, and I'm going to look at 2, 3, 4. And then I'm going to go to the next index. And then I'm going to iterate over all those elements that I've already seen again. So what you can see is as we are iterating, we are duplicating a lot of work because we are doing double traversals over the values that we have already seen thus far. And we continue doing this kind of duplicate work until we hit the very end of the array as we're iterating through. And that's really not the most optimal thing. So what we can notice here is that this is unnecessary iteration over elements that we have already seen. So what we're doing is we're getting rid of, in the sliding window technique, we're getting rid of duplicate work, and we're just sliding in a more linear time, right? This approach, the naive approach, is going to be n by k, or better characterized as n squared, right? And we can optimize this to a linear time algorithm by using the sliding window approach because we're not necessarily duplicating work and we're not looking at values a second time. We're just subtracting values and adding values, subtracting values and adding values. But we are doing a linear traversal. We're never stopping the traversal, and we're never looking at values that we've already seen thus far. So that is the main benefit of the sliding window technique. Let's look at a very simple example before we dive into the recognition of these types of problems. And this is a very, very common example that elucidates this exact idea very well. This is the idea of the maximum sum of a contiguous subarray. So the problem statement, as you can see on the screen, says we need to find the maximum sum of a contiguous subarray, which is essentially going to be some subset of this array that you see on the screen, some smaller subsection, if you will. And they're telling us that we have a fixed size of 3. So if you think back to what we were just looking at, this is going to be the fixed variant. So the window is not going to dynamically resize. It's going to be definitely fixed on this 3 value. So we have 2 criteria here. We're trying to find the maximum sum, and we're also constrained to the fact that we fixate the window size to 3. So if we're thinking about, from a very high abstract point of view, how we would maybe devise an algorithm is we're going to need to keep track of the current running sum, which can be initialized to 0 because we've added nothing, right? And then we're going to keep track of the maximum that we have seen thus far. So since we're trying to maximize the value, we can initialize it to negative infinity, which is basically the worst value that we can imagine. We want to basically continuously ask the question, is what I'm looking at right now in the current running sum, is that better than the maximum I've seen so far? So let's go ahead and walk through this example. So first, I need to get my window size to the size of 3. So I'm going to grow that. So I get to 3, and while I'm growing it, I'm keeping track of some running sum. So I get to the point where I'm 7. We've asked the question, is 7 greater than negative infinity? It is. So what I'm going to do is I'm going to slide this window over. If we're thinking from a programmatical or implementation perspective, to slide this window, we essentially need to subtract away the 4, and we need to add in the 7 to our current running sum. That's really it. And we'll look at the implementation in a few minutes, but that's effectively just going to look like we're sliding the window over. And that's where we start to get the name, the sliding window technique. And you'll see 217 yields us a sum of 10. So that's our current running sum. And then we ask the question again, is 10 better than our previous value, which was 7? It is. So we update the value and we continuously slide. And you can see we're doing even better. And we slide again. Well, you just notice that we just slid the window again and we didn't change any values. Well, for one, the current running sum maintained the exact same value, but that was not better than 16. So we just continue. You see, this value has actually gotten worse. The current running sum has shrunk, but 11 is not greater than 16, so we just keep our maximum recorded as is, and this iteration process continues until we reach the very end of the array. And what we would do in this case is the maximum sum of this particular problem of a contiguous subarray of size 3 would indeed be 16. And if we look at this from a complexity analysis standpoint, you can see that we have a linear time algorithm order of n, where we're basically looping through n number of elements, no more, no less, and that is the optimal solution to solving this particular question. So hopefully we understand the abstract idea of the sliding window. We've talked about the pros of using it from a time complexity reduction perspective, but now I want to talk about how to recognize these problems in the wild. How do we find these types of problems and know right off the bat, hey, this would be a really, really good candidate for the sliding window technique. And the first thing to note is that typically these problems are really well suited for iterable items. So things we iterate over sequentially. And that's really one initial dead giveaway, because what we're concerned with is we are concerned with the contiguous sequence of elements. So the contiguous sequence of elements. And when we're talking about contiguous sequence of elements, we're talking about items that are grouped together next to one another, right? So they occur maybe in the middle of the array, maybe not, but it's a subarray or a subset that occurs one after the other. And that is typically what we are looking for. And of course, we know that these are good with strings. We're talking about arrays of integers or characters. And even linked lists, right? Linked lists are not allocated in a contiguous way from a memory perspective, but you can iterate through them in a contiguous way, just like you would arrays or strings. So those are good as well. Now, in terms of the way that the questions are going to be asked, or the types of algorithms you're going to come in contact with, is basically essentially a variety of things, but it's the type of criteria that we're looking at. And it typically deals with trying to find the minimum of something, the maximum of something. If we're trying to find the longest thing, if we're trying to find the shortest thing, or we're just trying to figure out if something is contained within a given string, within a given array, etc. So we're trying to find the min, max, longest, shortest, whether it contains the following characters, etc. And we'll look at a wide variety of examples and also solve all of them today. But the idea is that we're trying to calculate something amidst these types of questions. So, maybe we need to calculate something. In the example that we just looked at, we were calculating the max sum. This is also a useful technique for something like the running average, etc. But the idea is that we'll probably need to calculate and record some value. And it's going to typically be the minimum, maximum, longest, shortest, or containing value within the input. And the thing to really remember is that it's all going to be contiguous, it's all going to be sequential, and these are the questions or types of queries against the data structure that we need to be aware of or cognizant of. Okay, so I want to talk about the different variants of problems that we are going to be solving today, and hopefully that we can solve these relatively quickly to keep this contained in one video. But the first is what we talked about before, and it's the idea of the fixed length variant. So if we just go ahead and type in fixed length, that's the problem that we kind of just looked at, right? We had a fixed length of size 3, and we were trying to maximize the sum. So the max sum subarray of size k is definitely a good variant for the sliding window technique of the fixed length. Another one is the dynamic variant. So we haven't looked at one of these yet, but we've talked about the abstract idea, and I just like to label this the dynamic variant. And this is basically a window that's not necessarily a fixed size k. It can grow and shrink like the caterpillar example that we looked at. And this could be something like we're trying to find the smallest sum that's greater than or equal to some value. So let's just say smallest sum that is greater than or equal to some value s. So you can imagine an array. We're trying to find the smallest sum of any window size at all, but the window that we are dealing with has to be greater than or equal to some value s. So we're essentially trying to find a window that gets as close as possible to the value of s. And we'll look at how to solve that problem as well with some sample data. And the final one that I like to think about is very similar to the above. It's the dynamic variant. So we'll say dynamic variant, but it typically introduces what's known as an auxiliary data structure. So we'll say with auxiliary data structure. An auxiliary data structure is just a fancy way of saying that we introduce something like a hash map or a hash set or an additional array outside what you would see as just a standard variable or Boolean flag. So we'll say dynamic variant with auxiliary data structure. And this is where these types of problems start to get really interesting. So the types of problems that we could ask with an auxiliary data structure could be something like, we need to find the longest substring with no more than k distinct characters, which is part of the criteria. Substring, which shows sequential data, and then k distinct characters is the other constraint. And maybe since we're dealing with distinct characters, we'll need something like a hash map or a hash set that can actually track the existence of characters and how often they have occurred in the given input string. So that's kind of the auxiliary data structure we would be dealing with there. And the final one that we'll look at is string permutations. So you can imagine that we're given a large input string and you're given another subset of that string or just another string, and you're basically asked, does that second string exist as a permutation of the parent string? So these are all questions that we're going to look at today. But what I want to talk about that matters even more than this is, what are the commonalities, right? What are the commonalities or similarities between all of these questions, right? Because we're trying to devise an abstract algorithmic mental model to solve all of these questions. And the first one that you'll see is everything is grouped in a sequence. So when we're seeing substring, when we're seeing smallest sum of a given subarray, so subarray, these are dead giveaway kind of keywords that we want to look for that show sequential groupings of data. Those are common for the sliding window technique. The next thing that we're looking at is everything specifies to some sequential criteria dealing with what we talked about before, longest, smallest, contains, right? So permutation would be contains some characters. And we can also have basically, smallest sum, subarray, we're trying to maximize something, we're trying to minimize something. These are all dead giveaways and commonalities between even just this small subset of questions that cover a wide variety of the sliding window problems. So what we want to remember is we want to look for essentially one or two criteria points and fixate the window around that. So we want to, look at this one and say, hey, we're trying to maximize the sum and the size is k. We're trying to, minimize the sum, and then the criteria is going to be greater than or equal to s. This one is going to be, we're trying to maximize or find the longest substring with no more than k distinct characters. And then string permutations is, we're just trying to find existence of an input string against another string. So these are all very common themes that you will see in the sliding window technique. So let's dive into the implementation right now to understand it. All right, so the first problem that we looked at was the max sum subarray, and this is a really good candidate to get introduced to the sliding window technique. Just to recap the example that we looked at before, we basically were given an input array like so, and we needed to find the max sum subarray, or basically a subsection of this array that yielded the largest value of size k. So the window length, like you can see here, this highlighted value would be size k, and we need to maximize this window as we iterate through and return the maximum value that we have found. So as we determined previously, The example input yielded a max value of 16, which we can see here, and the size of k was 3 in our example. So what we're going to do is we're going to create a method signature, and we'll just say public static int because we're going to be returning the sum, and we will say find max sum subarray. It's of course going to take in the input array, we'll just call it array, and then an integer value of k. So what we need to do is first we'll pass in some sample data. So we'll say, all right, let's just print out the call find max sum subarray. The integer array will be a new integer, and we'll give it the values that we see above that we used before. So we have 4, 2, 1, 7, 8, 1, 2, 8, 1, 0, and the value of k was 3. So that was the length of the window. So this should tell us basically the max value that we have found so far, and now we need to actually write the algorithm. So if we look back at our notes here, we said that we had a current running sum that we could keep track of that could change, and then we recorded the max value, which is the thing that we actually want to return at the end of the day. So if we go back to our code, we can note that. We can say, well, let's say that we have some max value, and that's going to be initialized to a really small value. So before we said negative infinity, in the world of Java, we'll just say integer.min value. And then we'll say, the current running sum, so current running sum that we talked about, is just going to be initialized to 0. So now we need to think about this in terms of what we were actually solving. Well, first thing that we had to do is we had to grow that initial window length, right? We had to get to the point that we even have 3 elements in our window. So if we go back here, what we can do is we can say, all right, we're gonna start a for loop and we'll initialize at 0, and we'll just loop until the very end. Because like we said, the benefit of this is that we are a linear time algorithm. And the first thing that we can say is, all right, let's just go ahead and add our value to the current running sum. So how we're going to do that is we're just going to add the current value to the current running sum, which is going to be the array at index I. But now we need to actually ask the question, is the current running sum greater than the max value that we currently have recorded? The way that we do that is we say, all right, is the value of I greater than or equal to, right? Is the value of I greater than or equal to the value of k minus 1? Now, why is this the question that we're asking? Well, first of all, the value of I says how far we are in the array. The value of k in our case is going to be 3. So if we look at the example input above here, when we get to the point where we're at k minus 1, we are at the second index, right? Which effectively says that we have 3 elements in our list. Now, once we have 3 elements in our list, we need to now compare the current running sum to the max value. So all we do is we say the max value is going to equal the math.max of whatever we currently have compared to the current running sum. And that will update accordingly. And now we need to do the part where we basically subtract away the 4 and we add in the 7. So how do we do that? Well, the first thing we need to do is we need to subtract from the current running sum that 4. So what we do is we say current running sum is going to subtract the element from the input array. So the input array is ARR. So we're going to subtract from that the value of I minus, and then we're going to subtract k minus 1. So what does this actually mean? Well, this says we're getting to the point where we're at I, and now we want to subtract the furthest right value that's going to violate the criteria that we have a window size of 3, right? If we're going to add a 4th item into the list, we've violated this constraint of 3, so we need to get rid of it, and then we will continue the loop. Once we're done, what we can do is we can return the max value, and that will be basically the criteria. And this is all we need to do. And if this seems confusing at first, we'll look through a few more examples, and you'll start to see that the code is pretty much identical regardless of the problem. It's pretty magical, and there's a lot of benefits to this type of algorithm, but let's go ahead and run the actual code. So you can see here we get a value of 16, and that is indeed the current maximum, or the best that we can do within this input. So let's go ahead and look at another example. The next problem that I want to talk about solving that we talked about before is the dynamic variant, where basically the window is not a fixed size, but it can change. So before we write the code, I want to conceptualize the idea from a higher abstract point of view. So imagine we have a similar array to like what we saw before. The problem statement says we need to find the smallest subarray with a given sum. So what we need to do is we need to find the smallest subarray that exists within this parent array where the sum of values is greater than or equal to 8 in this case. So if we think back to our criteria, if we wanted to recognize if this was a sliding window problem, we see that subarray tells us that we're dealing with contiguous or sequential elements or members of a given data structure, and smallest is the first criteria. We're trying to minimize something. And then the given sum is the other giveaway, right? So basically we want to keep in mind we're trying to find the smallest value greater than or equal to 8. So let's start through this animation here. So we start at 4, that's not greater than or equal to 8, so we can't do anything with that. 6 is also not greater than or equal to 8, so we can't do anything with that. Now we get to the point where this actually equals 8 exactly, so the smallest subarray size is 3. So now we ask the question, can I do better than 3 with the current data that I have? So I'm going to shrink the left-hand side. So once I subtract the 4, my sum, my current running sum, has actually reduced to 4. So I've already violated the criteria that I need to be greater than or equal to 8. So what I'm going to do is I'm going to grow the right side again. And now I get to the point where I have a sum of 7, 8, 9, 10, 11. So that's actually greater than or equal to 8, but it does not beat out the small subarray size of 3 that we have already calculated. So I try and shrink the left side, and we can see that 9 satisfies the criteria of greater than or equal to 8, and it was also smaller than the smallest subarray size of 3, so we update our value. I'm going to try and shrink this even further, and we see that 7 unfortunately violates the constraint, so now we continue growing the right-hand side. 15 satisfies the constraint, but it's not better than 2, but now we say, hey, maybe I can shrink the left-hand side. So we get to the point where we shrink it, and now we have just 8, and we have beat out the smallest subarray size of 2, and now we are at 1. This is actually the base case because we can't do better than one single element. We have hit it right on the head, so we can actually terminate the algorithm early. But in the case that we didn't exactly hit the value, we would do the same exact idea until the end of the array. And this is exactly what we need to code. And as you can see, this is different than the fixed window length because the window is dynamically resizing as we recompute. All right, so what I've coded up here is just the method signatures for the algorithm that we are going to implement. What we want to end up doing at the end of the day is we want to print out the smallest subarray size such that the value is greater than or equal to 8, and we're using the same input values that we used in our example. So I'm just going to call smallest subarray. I'm going to pass in the target sum, which is 8, and the input array. And the idea is that we yield just a value of 1 because we do indeed have one single value here. So in order to start programming this, we need to basically have the initial iteration that we talked about. So we're going to think about this. If we look back at our example, we kind of have this window, right? We're never stopping the traversal to where we're iterating one element at a time to the very end. So that definitely says that we can have a for loop. But what is changing is the far left value changes, right? So that tells us that we kind of need another index that grows, that basically stays static and then increases as we want to shrink that left-hand side. So maybe we have a window start and a window end, and the window end is the thing that's always iterating toward the end. So I'm going to go back to the editor. I'm going to say for int, and we'll just call this window end, and we'll initialize it at 0. But we're going to ensure that window end is less than the length of the array, and we're going to continue iterating through it since we have a linear time algorithm. And we're basically going to have a starting index as well. So we can call this, maybe we want to call it window start. That seems like a reasonable variable name for that. And similar to what we had before, we want to have a current running sum. which is basically going to be the sum of the current window that we're dealing with. So we'll just call this current window sum, and we'll initialize it to 0. And then the thing that we actually want to return is the size of that window. So we can just have basically an int min window size, and this will be initialized to some really large value because we're trying to minimize it. So imagine we're looping through the array, and the first thing that we can just continuously do is we can say, well, the current window sum is going to get the addition of the array at the current index. So we're just going to keep adding values in a linear fashion. But the second that we actually exceed the value, or we're greater than or equal to the target sum, that's when we need to say, can I do better? Can I do better? And we're going to continuously ask that question. So this is candidate for a while loop because we're going to end up shrinking the left-hand side. So what we say is, okay, if the current window sum is greater than or equal to the target sum, so if we're greater than or equal to 8, what I need to do is I need to record the best that I'm at so far. So I'm going to say the min window size is going to be the math.min, because we're minimizing over these values. It's going to be the math.min of my current min window size, and then we're just going to take the window end minus the window start, and we're going to add 1 since the arrays are indexed at 0. So this is basically going to give us the delta of how large our window is exactly. And then what we need to do is we need to basically say, since we're going to remove the value on the far left of the array, like we saw in the example, I need to subtract it from the window sum, very similar to the previous problem. So I'm going to say current window sum, and I'm going to subtract from the array the window start index because we're getting rid of it. And since we want to basically shrink from the left side, then I'm going to increment window start. So if we look back at our example, we are growing, and then now we want to get to the point where we're greater than or equal to 8. So while our criteria is satisfied, let's try and minimize. So we're going to want to shrink that left-hand side. See how we're shrinking the left-hand side. So if we look back at our code, this process right here, where we're subtracting the pointer at the far left-hand side, is the shrinking process when we subtract it from the current running sum and then we increment its location. So once we do that, we can get to the point where we just return the minimum window size. So that's going to be min window size. And as we had proved before, that should be 1 because we have found just one element. So I'll pass in target sum here, and we'll go ahead and execute the algorithm. And you can see we have the value of 1. All right, so there's one more problem I want to look at, and it's the usage of the dynamic variant, but with an auxiliary data structure, which adds slightly more complexity to these types of problems. All right, this is the final algorithm that I want to cover to help elucidate the idea. This is the dynamic variant with the use of an auxiliary data structure. I'm going to leave the code for this one in the description, and we can just cover the conceptual idea, and I can leave it as an exercise to the viewer to implement it. So the idea is that we need to find the longest substring length with k distinct characters. In our example, k is going to be 2. And what this is saying is we need to find the longest, basically the longest contiguous sequence of characters such that the number of characters that are distinct does not exceed the value of 2. So there can be 1 character of a really long length or 2 characters of a really long length. But once we add a third character into the mix, we're violating the criteria. So back to our tips and tricks when we're thinking about this algorithm, we're trying to maximize, so longest is a dead giveaway, and then substring definitely gives away the fact that we're dealing with contiguous or sequential values in our buffer or our array. So that's a dead giveaway that we would want to use something like the sliding window technique, and we can optimize this to a linear time algorithm. So what we're going to do is we see A into the mix, so I'm going to add that into my hash map. That's going to allow us to keep track of our character counts, and we're just going to grow the window. A goes to 2, and I'm going to continuously update my max because I'm getting better and better here. We get to 3. That's even better than the 2, so I update that as my max. Now we add H into the mix. That does satisfy the fact that we do not have more than 2 distinct characters. So I add an entry for that. And then it increments to 2 because now we have 2 occurrences of H, and our max substring length right now would be add 5. So what I'm going to do is I'm going to add I into the mix. So I add I, and you can immediately see that what has happened is we have violated the constraint because we have 3 values. So what we need to do is we need to shrink the left value. So I've shrunk an A, and I've decremented its occurrence count to 2 because we've gotten rid of it. We're still violating the constraint, so I'm going to shrink it even more. It gets decremented to 1. We still have more than 3 characters, so I decrement it even further, and now it's at 0. So to help us, what we're going to do is we're going to remove A from the hash map completely, so we're going to delete it. So now we have only 2 entries. So now we're good. 3 does not beat out 5 though, so we're not going to update our max, but we're going to grow the right-hand side. We've added B, and we can see that we have violated the constraint, so now we need to shrink H, and it decrements to 1, and now we're still violating, so we shrink it even further. It decrements to 0, so now we say, let's go ahead and remove it completely. So we delete it from the hash map, and then we grow again. And as you can see, we violate again. So we shrink, I goes to 0, we remove it, and the right-hand side has reached the end of the array, so what we're going to do is terminate and record the maximum length substring we have found thus far, which in this case would be 5, corresponding to AAAHH. So that's it for this video. Those are basically some example problems that follow the technique of sliding window. I'm going to leave the code for all of these problems that we covered in the description, as well as some external resources to help you study this concept a little bit further. If you guys have questions or want to understand more algorithmic mental models, feel free to leave a comment, and thanks for watching.